beginning this lecture, I'd like to preface it by mentioning that this is intended for an undergraduate pedagogy program, so this is one lecture as a small part of a larger pedagogy curriculum. So, before we begin, I'd like to present you with a map of how we're going to go about this lecture. So first, I will present to you a brief definition, as well as the prerequisites of sound, the necessary components that are needed for sound. So a discussion on the nature of sound, followed by the anatomy of sound waves, so why we graph sound waves as we do. And after that, we can go into the elements of a musical tone. So first, here is a working definition of what sound is. As you can see, I've highlighted some of the key terms so that we can tease out the 4 prerequisites of sound. So sound is an oscillation of pressure that is transmitted through a medium and perceived by our ears. I hope to make this a little bit interactive, so I'll be asking a couple of questions. Feel free to answer if you feel comfortable doing so. So from this, we have at least 3 components. Can anybody tell me what those 3 components are? So first we have, I'll start. First we have the ears. So something with which to perceive it with. And then we have a medium of which the sound wave is propagated. And then we have an oscillation and pressure. Now if we look at oscillation and pressure, we can see that that oscillation and pressure has to be caused by something. So that would be probably an object that's vibrating, a vibrating object. And this vibrating object can't vibrate by itself. It has to have something that is making it vibrate. So we need an energy source, a vibrating object, a medium of travel, and something with which to perceive it. That can be the ear, or a microphone, or any input of a system. So the energy source, to review, sets the vibrating body in motion. The vibrating body, as you can see with the animation, displaces the molecules in the medium of travel, and the medium of travel thereby propagates this oscillation of pressure to our ears. You can see I had a lot of fun with this. So one more time to review. The energy source sets the vibrator in motion, displacing molecules in the medium of travel, and finally transmitting it to a perceiver, or our ears. Any questions thus far? Great. So, as per that animation, we can see that the air around us is composed of several particles of matter called molecules. And these molecules have a certain characteristic about them. They tend to stay a certain distance apart from one another. So, when we push these molecules together and let them go, they tend to come back to the original distance of which they started. So that's called compression. And when we pull them apart, they also tend to go back to the position of which they started. That's rarefaction. So as you can see, this, I don't know if you can actually see all the black dots are meant to represent a molecule. And some of the black dots are actually highlighted in red. And the only reason they're done so is so that you can actually track them, so you can look at them and see what actually they're doing. So it appears as if a wave is moving from the left side to the right side, right? But actually, if you look at the red molecules, which they're exactly the same as the black molecules, they're actually not moving from the left side to the right side. They're just moving back and forth. So what you should get from this is that the oscillation of pressure does not mean that the molecule is moving from the vibrating source to the perceiver. It just means that they're being displaced. So consider a slinky. Does everybody know what a slinky is? So if you have a slinky and you just lightly tap on one side, each spring compresses and rarefies, compresses and rarefies. So it seems that the pressure oscillation is moving from the place where I tapped it to the other end of the slinky. But in actuality, each spring is not moving from one side to the other. So this is how a wave is propagated through a medium. Now the elasticity of air is such that within 1 second, this oscillation of pressure reaches 1,100 feet. So another way to look at that is that in normal temperature, because we know that pressure varies with temperature, that sound wave travels 1,100 feet per second. That's pretty fast. So although this graphic shows that a linear progression of the wave, when you the way that a wave is propagated is circularly. So if I have a sound source, it will be not only transmitted from one end like a slinky to another, but it will be transmitted all around, all the way around. So that's why I said it will have a radius of 1,100. So now we saw that sound waves look like this on the right. So why, when we graph it, does it look like that? So this is what we call as a longitudinal wave. But when we graph it as a transverse wave. Does anybody have any guesses why we do that? Or what does it represent? Yes?
Is this squiggly line just one molecule or no?
No.
Never mind.
So, okay, let's line them up. So each place of compression, here's a, if I can figure out there we go. So each place of compression corresponds to a peak in the transverse wave, and each place of rarefaction corresponds to a place of a trough in the transverse wave. So we graph this on an x and y axis, as how we graph many things, and the compression represents a peak, and the rarefaction represents a trough. So what do these x and y axes stand for? Any guesses? Well, we know that, here's a hint, we know that the compression and rarefaction can't all happen at the exact same time. Yes?
So is it amplitude and time then?
Yes, so amplitude is a very general term. So amplitude in terms of, if we go back to our definition, sound is an oscillation of pressure, right. So pressure is a specific type of amplitude. So we have time on the x-axis, the horizontal axis, and pressure on the y-axis, the vertical axis. So now that we know why we graph waves as we do, waves that repeat themselves, that they have, when you graph it, we have corresponding compression and rarefaction. And these repetitions in compression and rarefaction, no matter, they don't have to look like exactly like this. This is a sinusoidal wave. We'll get to that later. So cycles that repeat themselves, they are labeled as a musical tone or a periodic sound. And things that do not repeat themselves, they have a random, irregular pattern, are labeled as an aperiodic sound or noise. So, as per what we just discussed, any guesses to what these sounds are? So the first example, do you think that's a noise or a musical tone?
Musical.
Musical tone. And why?
It's written.
Yes, because it's regular, right? It repeats itself. So we can see that even though we have a bunch of squiggles, after this point, it's a repetition of the same squiggles, right? So we have a cycle that repeats itself over and over again. So this is actually a plucked guitar string, and we have that as a musical tone. And the second example is noise, right? But I chose this example because even though this is noise, it's coming from a musical instrument. It's actually a cymbal crash. So musical instruments can be capable of producing noise as well. Right, so the simplest musical tone is called a sinusoidal wave, and sinusoidal refers to the type of motion. And it is a motion that is represented by a simple pendulum or a simple mass spring system. The law of the pendulum, how many people are familiar with the law of the pendulum? Okay, well, this is a good story then. So Galileo was sitting in church one day, and the legends say, and he was noticing that some chandeliers were swinging further, had a deeper arc, and some chandeliers had a smaller arc. due to the wind from the windows. So as he was sitting there and looking at the chandelier swinging, he noticed, obviously he must have been bored with the sermon, I guess, but he noticed that the chandeliers that had a wider arc still took the same amount of time to come back to the equilibrium as the chandeliers that had a lesser arc. So he posited that no matter the magnitude of displacement, the frequency is independent of it. Now, if you change the length of the chandelier, that's a different story altogether, though. Now, so the law of the pendulum basically states what you need to take away from this is that frequency remains the same regardless of the width of the arc for which the pendulum swings. So a tuning fork, it also moves in a sinusoidal fashion as well. And any mass spring system, as I mentioned before, also moves in that fashion. And a sine wave, normally the sounds that we experience in the world today are complex tones. Sine wave is a very simple tone. We might remember it as a test frequency or an emergency alerting frequency. So here's how it sounds. I hope it's not too loud. I don't know. Okay. Yes, that is a sine wave. It's very it feels different when you listen to it because it's a very sharp, pure tone. So now that we know what the nature of a musical tone versus noise and the simplest musical tones, we can now discover the 5 essential properties of a musical tone. So before we begin, I will just list them, and then we'll go more into depth. First is pitch. Second is intensity. So pitch is the perceptual correlate of frequency. So how many times this period happens within a set amount of time. And that's what we perceive as pitch. Intensity is the amount of displacement. So when we talked about the Galileo example, how much the chandelier is displaced from equilibrium. The duration is simply put time. And timbre refers to the quality of the tone. Why we perceive a clarinet as sounding different from a violin, or a voice sounding different from a piano, the timbre. And the fifth is a borderline concept that some scientists advocate as sonnets, like Carl C. Shore and William Bernard also advocate sonnets. Sonnets is, it accounts for fluctuations in frequency, pitch, and intensity. Frequency, intensity, and timbre. Pitch and frequency. First, we will discuss pitch. Pitch, as per the image here, we can see that low frequencies are indicated by a wider meaning more time between each cycle. So we have the compression and rarefaction happens further apart from each other. So pitch is what we perceive as frequency, and it's measured in cycles per second. So how many times this happens in a set amount of time, which is a second. So when a singer sings an A above middle C, so an A 440, the singer's vocal folds vibrate 440 times in the span of 1 second. So 440 times in the span of 1 second means that the vocal folds vibrate the molecules around it 440 times. So compression or rarefaction happens that fast. Intensity is basically, as we mentioned, the amount of displacement, how compressed are the molecules, how much the chandelier is moved from the point of equilibrium, how much the eardrum is indented, and how loud. Now, I would like to go back and just say one thing. Frequency is directly proportionate to pitch. However, intensity is not directly proportionate to loudness, because the ear works in such a way that the ear adjusts for itself. So loudness is expressed in the units decibels, and it's not a unit, it's a ratio. There's several types of decibels, dB, SPL, dB, HL, and it is also expressed in fons and sones as well. However, the decibel scale, deci stands for 10, and bell is Alexander Graham Bell. It's a unit named after him. So the decibel scale is a logarithmic scale, base 10 log scale. And basically what that means is that since the ear adjusts itself, doubling the intensity doesn't double the loudness. So the ear has a function called amplitude compression. So in order to protect itself from very loud sounds, when we double the intensity of the sound, it doesn't double the loudness. The point of displacement for the basilar membrane is actually much less than what we had. So in order to denote this, the decibels, a 10 decibel increase means 10 times the energy, a 20 decibel increase equals 100 times the energy, and a 30 decibel increase equals 1,000 times the energy. That was a little fast. Any questions about that? Okay. Now this graph here is called an equal loudness contour. And what this shows, actually, so we have the two axes. The x-axis shows frequency, and the y-axis shows sound pressure level, so the intensity. Here we see that this bottommost line here is the threshold of human hearing. So basically what this shows is that the human hearing, the range of human hearing is from 20 to 20,000 hertz, and the most sensitive area is right here, from 1,000 to 5,000 hertz. So we hear these sounds more easily than we hear these sounds, which means that this much more energy is required for these sounds to be heard than these sounds. So higher sounds are easily heard more than lower sounds. So basically, the lower and higher frequencies require greater amplitude to be perceived as equally loud. Is that clear? Duration, I can't really say anything much about it, but it's basically time. In some instruments, don't let this confuse you, they say that duration is related mathematically to amplitude. That just means that the harder you hit a gong, the longer it sounds. So that's not really, that's a pretty obvious concept. So timbre is, we mentioned it briefly, why do these sounds have, we mentioned a sinusoidal wave, and that is a very regular fluctuation of compression followed by rarefaction and then compression again. But why do these waves, even though they're musical tones, have quavers? So timbre, is distinguished by the waveform. So why do they have, does anybody have any guesses of why the sound wave has quavers? Yes?
All of the things that vibrate have some sort of substructure, so that substructure also vibrates and makes harmonics that make the waveform more complex.
Right, exactly. So this guy here is Jean-Baptiste Joseph Fourier, and he said that any complex sound wave can be taken apart into a bunch of simple sine waves. Any complex sound wave, I meant to say complex tone, can be broken apart into a bunch of sine waves. So basically, most of the sounds that we hear in life are complex, and they're composed of several simple pendular tones. So as we can see here, so we have one sine wave, and we add another sine wave to it in equal phase, and we get this as a result. So now the shape has been adjusted because of constructive and destructive interference. And now we have something like this. We add another sine wave at the third partial, and we have something that looks like that. We add another partial, and it changes the shape, keeps changing the shape until it looks like this. Now this type of wave is known as, well, it's not a sawtooth wave. This is the opposite of a sawtooth wave. A sawtooth wave would look like this and then have a sharp cutoff wave. The reason why sawtooth waves are important is at first approximation, the sound that is made from our vocal folds before it is influenced by the vocal tract resembles a sawtooth wave. And that's because the closing phase of the vocal folds are much faster than the opening phase. So it has a sharp cutoff. So that's why sawtooth waves are important. So as we can see here, notice that in this example, that the partials decrease in amplitude as they are added. So that means the higher the partials go generally, they decrease in value. Now, the different waveforms have different strengths of their partials. So a harmonic analyzer basically separates this complex tone into these various components. And actually, what our ear does is actually much the same as that. We call that analysis Fourier analysis in honor of Jean-Baptiste Fourier. And our ears actually do that. When we hear a complex tone, each part of the basilar membrane responds to these different frequencies. And then our brain puts it back together as a complex tone. So now, so basically we said that the different harmonics, the various strengths of the different harmonics influence the waveform, right? And influence the particular quality of the tone. So this is the harmonic series. This is an image from William Bernard's Singing the Mechanism and Technique. And I thought this was a really amazing image because this shows the harmonic series as it relates to the evolution of music. So here we have the octave, and he writes on the side Greek monody. So, and then we have organum as the fifth, and then the diatonic modes, the major triad, the ninth, and the tertian chords, and shows how harmony has evolved throughout time and throughout the harmonic series. So basically what we need to get from timbre is primarily determined by the relative strengths of various partials. So different types of waves have different partials that are strong. So a square wave, it looks just like a square actually, just like that. And that is the sound that is almost similar to a clarinet. And the sawtooth, as I mentioned earlier, is that first approximation to glottal pulses. Now this is the harmonic series, just for you to hear. Great. The last concept is known as sonance. And sonance basically refers to fluctuations, as I mentioned earlier, over a period of time. This is a borderline concept because not all theorists, not all scientists agree with this concept of sonance and what actually it consists of. So basically, it's fluctuations in intensity, timbre, and pitch. But it also involves noise factors, such as consonants and other noise factors as well. So William Bernard says that the longer someone sings, or the longer you hear his tone, the easier it is to distinguish between other tones as well. So while timbre is like a simultaneous fusion of sine waves and simultaneous fusion of tones, sonance is like a successive fusion over a period of time. So the greater the duration, the easier it is to distinguish between two tones. And that's facilitated by the sonance. Any questions about the sonance? This is a borderline concept, so this is, take it as you will. So to review, basically, a sound wave is an oscillation of pressure caused by a vibrating body, transmitted through a medium, and perceived by our ears. Regular sounds are perceived as musical tones, and irregular or aperiodic sounds are perceived as noise. The 5 basic elements that we described are pitch, intensity, duration, timbre, and sonance. So some sources for further reading include, these 3 books are very beautiful, they provide a solid foundation in acoustics, but from 3 various perspectives. First one is from a pedagogical perspective, William Bernard Singing the Mechanism and Technique, a solid foundation. And Hodges and Siebel's Music and the Human Experience. This is a psychological perspective for music psychology. And William A. Yoff's Fundamentals of Hearing is an audiological perspective of it. And all 3 books provide a really strong basis in acoustics. So if you're interested in this, please go ahead and read more about this. Thank you very much.